Yeah, so good morning, everyone. Welcome to here, I guess the second full day of the conference. I hope everything's going well. I'm excited to talk about something that's kind of near and dear to my heart and near and dear to the hearts of several folks in this room. Specifically, it's like how do we make FHIR work well with a bunch of different SQL-based tools. So just for a little bit of background, I'm a software engineer at Google, but for folks who know me, you might be aware that I have an arguably unhealthy obsession with making FHIR data work well with analytic databases across a variety of tech stacks and a variety of employers that I've been with over the last several years. And that hasn't diminished at all, so I'm excited to be in this space, and now that we have some real momentum here. And I think that we can kind of sum up really the learning objectives is really one thing. Really, there's this, we want to share a draft specification that we hope will make FHIR work easily and well with a variety of analytic tools, whether it's SQL-based or otherwise. We want to and we also want to do a call of participation. So for folks who might be interested in this space, as you go through this spec, I'd really encourage you to think about, as we navigate this, think about how it might apply to a problem you might have. So presumably, folks in this room have some interest in some form of analytics over FHIR data since you're here. And we'd love to understand is like, will this help solve your problem, or what other areas could we jump in on and contribute to? So with that, let's go ahead and jump in. So the very first question one might have is like, why not just take the FHIR data and store it directly within an SQL engine? After all, SQL engines these days are pretty powerful. You can directly, a lot of them have JSON support, a lot of them have like complex nested and repeated structure support. There's a lot that you can do with this space. And in fact, that was the approach that we took in an earlier iteration of this. But it has some downsides. And here's a few of them. So a lot of times in this talk you might hear us referring to SQL on FHIR V2. Well, the V1 was essentially taking FHIR and mapping it into an SQL schema. But we found a bunch of different trade-offs, so depending on the needs and depending on the tech stack. The first one that comes to mind is some workloads really wanted a simple implementation where we could take FHIR JSON, put it in a database, and work with it there, which is great. It's much easier to deploy. It's widely supported in a variety of different databases, but it has some downsides as well when contrasted with a system that would take FHIR data, break it up into individual columns per field, and then run queries over that. And so there's this immediate trade-off. It wasn't obvious. There wasn't any right answer to that was suitable for all workloads. So there's not like a common FHIR representation in a database that meets everyone's needs. So that's like one immediately challenge to trying to have some sort of standard SQL representation of FHIR in a database. And even if we did have that standard, there's still a whole lot of variance in the SQL engines between and how they work together. So depending on the SQL engine, if you're using an expanded set of fields to query things, you might have a cross-joined nest structure in order to expand nested fields, or a lateral view explode, depending on your engine. If you're using a JSON engine, the SQL dialects between JSON still vary significantly. Now, granted, I mean, this stuff is trying to be standardized through the SQL engines. There's things in flight, but in practice, I think we found very early on in these efforts is that writing SQL over this complex data structure was not portable between systems. And as a result, it kind of doesn't achieve one of our fundamental goals, which is kind of reuse of FHIR reuse of analytics across a variety of technology stacks. And finally, this stuff is pretty difficult to use, both in terms of expertise. If you're writing SQL natively, we've found like a lot of users that want to be able to query this sort of things struggled with the sort of nested structures and pulling it out in the repeated nature of it. And similarly, a lot of analytic tools work really well if you give them a flat table of data that you can join together, but they work a lot less well when you have deep, complex, non-tabular data. So we need to do something a little bit better here. And as a result, like starting last year, I think this was identified kind of independently by a few groups, and we started to come together. And the reality is that what we have in the FHIR space is we have this nested repeated structure here, which is great for a whole lot of workloads that we all use. But what users want, at least many or perhaps most SQL users will be looking for a simple table on the right there, where everything just maps cleanly to scalar values and columns. And really the whole essence, everything about this talk kind of boils down to this little arrow in the middle. where we're proposing an approach to take FHIR data and be able to convert it into this tabular form for a variety of different ways in a variety of different use cases. And this is kind of like the essence of it there. And we've intentionally constrained our aspirations to kind of be in this scope in order to be able to have a lot of reach to a lot of systems and a lot of technology stacks. So let's jump into how we're going to go about doing exactly that. So really the essence of this whole spec is what we call a view definition. And this is just for right now, we'll go into details about what all of this means. But given that this is the first time that most of this room has probably seen this little structure, I think that perhaps you can kind of see what it is. And you can perhaps kind of see how it would convert a FHIR resource into a flattened table, even though I haven't even shown what the flat table would look like. You can get an idea of of these key elements, what the columns might be, what the source resource is, what the target table name is. And as you kind of look through this, you're probably doing this mapping, but I'll go ahead and show the mapped version of it, but producing this flat table there. And then, of course, on top of it is whatever database, whatever analytic engine, whatever tech stack you prefer to have in this space could live right there. And I think this kind of boils down to it. So much of what we're trying to achieve in this space is to offer a standard way to author, to share, to reproduce, and to execute these mappings into flat table views over a variety of tech stacks. So let's take a little bit closer look about what exactly this is. What is this view definition that we're looking at here? And we'll go into it in a fair amount of more depth as we go in this space. So first thing we'll look at is we have just a table name. So very straightforward, whatever the table maps to. We have the resource that we're creating a view of. And we actually are very intentionally constraining views to be of a single resource, and we'll go into some of the reasons why as we proceed in this talk. Then, after we decide what resource we're starting with to create the view, we'll have one or more select stanzas. And each one of these stanzas basically pulls one or more columns from some part within the FHIR resource. So in this case, we actually have two stanzas. One is we pull for an identifier, and the second is we'll actually pull from the address field in the patient. We have the column names themselves, pretty self-explanatory. And then the paths that you'll see in here, every time you see a path anywhere in this spec, it is a FHIR path expression. The only thing we've added is that we've added a couple additional FHIR path functions that are convenient for this use case of projecting stuff into a tabular form. So you'll see in this case a get resource key, which essentially returns a primary key that could be used for the purposes of the table, or a key in general that could be used for a reference that uniquely identifies that resource so you can join to it in an analytic setting. There's a little bit of subtlety to this. There's a little bit of trickiness in order to do that well, which is one of the reasons why we kind of wanted to build a function for it and have some implementations. We'll go into that in a little bit. The next piece of this is that you'll see in a few places is because FHIR has quite a bit of repeated elements in different places, is that we want to be able to unroll tables often. So in this case, if we want to build a table of patient addresses, well, a patient may have more than one address, and we want to be able to expand both. And so for each, again, this is just a FHIR path expression. It points to the address field within the patient, and that essentially sets the scope for the select stanza in which it is placed. And then beneath that, we just have the sets of columns that exist in there. And most of these are just really straightforward. FHIR path expressions relative to the stanza that it's in, relative to the for each. If there's no for each, it'll just be relative to the root of the resource or a parent there. And I think that one thing that's worth mentioning is that you'll see on that very first one, the street name. If you're familiar with the FHIR addresses, then you'll know that street names are broken up into an array of line strings. But let's say in a target database, we just want to append them. But the nice thing about just building on FHIR path expressions is that we can just use the built-in FHIR path join expression to get that into a flat state. So this has a few nice properties in that by building on top of FHIR path, by having a relatively simple structure here, we found that this sort of specification is relatively easy to implement and scale. And in a bit, we'll go into, actually, in the session immediately following after this, there'll be a showcase of, I think, 4 distinct implementations of this, and there's a couple others out there of this draft specification. So we're kind of excited that we're able to get such momentum of this draft so early on. Now, I will touch on a few related efforts before I go kind of deeper into the specifics, deeper into the semantics of all this sort of thing. And I think folks may be naturally asking, like, there's some other options that I might use to solve similar problems, and why not use these? For example, if there's OMOP has a huge audience that's great for a wide set of use cases, and there are some existing capabilities to load FHIR into OMOP. And if that meets your needs, then I think that's great. I mean, absolutely use it. That said, like with everything else on this list, there are capabilities that we don't think are satisfied by some of the existing options, and hence the need for a way to approach this that kind of narrows that use case. So in this case, for example, in the OMOP case, for instance, not everything in FHIR is expressed in OMOP. There's context there that doesn't. Secondly, the OMOP schema is excellent for a certain class of problems, but there are other classes of problems in which OMOP may not be an ideal fit, an ideal schema. And so we believe that there are other ways that we'll want to convert FHIR data onto tabular forms. The second item that might naturally come up is, like, there does exist something called the FHIR mapping language, and that could be used. Now, the FHIR mapping language, I think, it tackles a much broader, much more general problem that also greatly increases the complexity and challenge of both implementing, of authoring, of understanding, of using. And so in that, the FHIR mapping language is capable of mapping between an arbitrary FHIR structure and an arbitrary other structure. And as a result, there's a great deal of complexity that results from sort of the nested rules and the recursion and everything that needed to express that. And so because the analytics use case, or the projecting onto the flattened table views, is something of like a special case, we think a simpler approach is justified here, given like the widespread need to perform analytics over FHIR data. And so we think that this is sort of a complement to the FHIR mapping language that's targeted to a use case that is much easier to implement and hopefully easier to author. And the final one that I'll call out here I'll mention DBT, but there's similar technology stacks. And we've seen a pattern emerge, and I'm guessing some of you in this room have used this pattern, of taking FHIR data, storing it as in JSON form or whatever form is appropriate for an underlying database, and then using like a pipeline of SQL functions to transform that underlying form into flat tables. And that pattern is, if that works well for your use case, then I think that's an excellent flow. And actually, I think DBT and that style of technology stack will continue playing a role here. There's a couple considerations to it, though, and that is, like, one, the initial steps of those transformations will still be very technology specific in order to get FHIR data into those flat views. Even with DBT, it's still SQL, it's still stack specific dialects and translations. The second piece is that I think as we get deeper in this sort of thing, we can concisely express a wide set of transformations over FHIR data with FHIR-Path, simply because FHIR-Path is an expression language specifically for that use case. And we'll see some examples of navigating deep into the FHIR structure, of selecting necessary elements that we need and expanding those out, all of which can be expressed in small snippets of FHIR-Path, which would otherwise be perhaps several or even dozens of lines of SQL. And so we feel like a FHIR-Path-based system is a really nice approach to do this translation. And as a result of that, I mean, I could see a lot of analytic pipelines if you work in a DBT environment, which I think is a great approach to many problems. This translation of FHIR to SQL may be the first step. We take your FHIR resources, we can use this mapping, we land it into that initial table that could exist in the database, and you can build your analytic or other pipelines on top of that using the technology of your choice, which of course, including DBT. And so, yeah, I think this kind of fits into the ecosystem. And of course, this is nowhere near an exhaustive list of data transformation tools, but I think we kind of took a sampling of a few of things here to kind of identify how we feel like this effort is complementary to tools that are much more general, like DBT, or more specific, like OMOP, and how we kind of fit into this tool chain. And I think that one thing I'll mention specifically in the OMOP space is that there is actually an effort to use this SQL and FHIR effort to actually build a scalable transformations from FHIR into OMOP as well, because as a stepping stone along that path. So I think that these are definitely complementary efforts from that space as well. So with that context, what we're going to do now is we're going to take a look. We're going to look at more of a zoomed out view of this tech stack for SQL and FHIR, and then we're going to zoom in on some of the details and how it all works. And so this is the zoomed out view for everything here. And we'll just kind of go through a couple of these quickly because I think it's important to look at this perspective and understand how it's framed in the context of the broader system. So starting let's start at the top here. So at the top here, we're intentionally non-prescriptive, and the system is entirely agnostic. It's whatever analytics tools you want to use, provided they work well over nice flat tabular data. We completely have no opinion on that, and intentionally so, because we want to be flexible. In the middle there is the view layer, and this is really the heart. This is almost the whole specification is the view layer itself. We kind of sandwich it in these other layers to provide context. And the view layer has these two pieces. One is the view definitions that we've already saw in that space, so this FHIR path-based configuration setup. And then view runners, which is just a tool or a system or a technology stack that translates view definitions into these flat tables. And I think you'll see in the following session there's a variety of options in this space. It can range from something more like an ETL pipeline to build a table that's actually physically manifested. We actually have some systems that will take these view definitions and apply them on the fly. So if FHIR data is stored, it'll create that view dynamically as needed from that space. The key is you can use the same view definitions, and you can choose the technology stack that fits your use case, that fits the performance characteristics of what you're looking for. And of course, that view runner needs to be built on something. And of course, this is where the data layer comes in. And again, we are agnostic about this. The data layer is just a lossless representation of FHIR data. It could be an actual FHIR service itself, if that meets your performance characteristic needs. It could be a bulk export of ND-JSON files used for a pipeline, or it could be stored in a JSON or a columnar structure in a database. The key is like we can author and reuse and build upon this view layer of content that exists there. So with that framing, I think we'll touch on one more sort of piece of the philosophy of this entire effort, in that when designing this sort of thing, there is a struggle between two competing needs. On one end, you have the desire for ease of use and ease of implementation, but that often competes with expressiveness. And I think that we kind of see that in some of the trade-offs that we might make between this SQL and FHIR, which is more narrow scope, but hopefully easier to use, versus a FHIR mapping language, which is more expressive, but has a higher complexity curve. And the approach taken with this project really comes down to is like, we really want to focus over on our efforts on this sort of ease of use, ease of implementation. Our goals are very much constrained. Let's take FHIR resources, let's unroll them into flat tables that meet your needs, and that's it. And then for all the powerful stuff that builds on top of it, use your favorite database engine. So to make that perhaps just a little bit more concrete, we'll list some examples of the trade-offs, of the decisions, of the options that we made while exploring this path. And it kind of boils down to just using the right tool for the job. So for example, we've intentionally chose that a view over a FHIR resource selects a single FHIR resource and expands that to one or more, or actually really 0 or more rows, because it can filter stuff out. Where it does not attempt to join across resources whatsoever or do any form of data aggregation whatsoever. These are things that database engines do really well, and the syntax and semantics and performance characteristics vary significantly between these. So as a result, we're going to leave this to the capabilities of database engines, because that's where their strengths are. And this also kind of boils down to what sort of native types you're using on the underlying system, what sort of high-level analysis or analytics you want to perform on top of that. Really, we're constrained is like convert versus to run view at a time and move things downstream. And so I think that sort of underpins a lot of this. All right, so with that sort of primer, I think we're ready to kind of jump into some of the heart of what's going on here. And the nice thing is like, so the view definition is right now, it is technically a FHIR logical model. So honestly, before getting too much in this effort, I was not really familiar with FHIR logical models. But you can kind of think of them as, but they're actually defined by structure definitions. They're much like a FHIR resource, they're just not formally included in the FHIR standard. We actually have a logical model that's in a structure definition that's part of this, and we're working through the FHIR community process to refine that. Similarly, using the same spirit as all the FHIR approaches, like we have very minimal top-level constraints on this structure definition. We want this to be sort of like a generic container, like that describes views that can be projected from a FHIR database. And then use profiles to narrow that down to meet those specific needs. And so one example that we'll see a bit later is like a view definition doesn't necessarily have to constrain itself to producing only flat tables. I mean, in fact, the base view definition does not constrain itself to that. You can have columns with complex structures that are produced from that view. But then we have a profile for a tabular view definition that adds that constraint, that requires simple flat tables. And so if you have a view that needs that, you can use that profile just for that. Therefore, sort of embracing kind of like the FHIR sort of thought process, the FHIR mindset of defining structures, of refining structures and constraining them for specific use cases. And yeah, don't worry if you can't read all this stuff on the side here. We're going to zoom in on that a little bit further. So let's break it down a little bit more. So there's a couple pieces to this. So I think the stuff at top is like there's a bunch of metadata and the names and the URL and the FHIR versions that are supported, a flag that says whether this is experimental. I'm not going to spend time on that. We have it all online. You can go read it if you're interested in that space. So I think that we'll go from there. But then we have the bottom bit here, which I've called the interesting parts. So I'm thinking let's dive into the interesting parts. So let's expand that. Yeah, so here's the kind of the core of these definitions, and really kind of boils down to just three major pieces. One, the first is pretty straightforward. It just defines name constants that we can reuse. So for example, if you have like a blood pressure LOINC code that you want to use to filter your view definition, you might define a constant for that and reuse that constant elsewhere in your FHIR path expressions in this. So just a way to define name constants that can be reused. The second section is a select stanza, and we saw that in our example before, where we could just select which columns that we have from the nest of that. And the final one is a where clause, where it's essentially all it is a list of 0 or more FHIR path expressions that allows you to filter down to the resources that you're looking for. For example, if you're building a view that only contains blood pressure observations, you might have a where clause that it filters down to those resources. So we're going to start by zooming in on the select expression itself. And this is really the entirety of the spec that we're going to jumping into here. So hopefully it kind of gives an idea of how we've sort of constrained this in a way that is actually usable and maintainable given these small settings. So the pieces that really boil down to is just a set of columns names. There's the column names, there's the FHIR path expression, there's a human description of it, and to define the column names. There's a few pieces of metadata where we kind of declare, hey, can this column name be a repeated field? Is it a collection? In the tabular profile we described earlier, it must be false, and that actually is a constraint the profile applies to narrow it down to only scalar data. And the actual type that is expected. And this is actually the FHIR type that expected here. And the nice thing about using that is that it allows us users to inspect a view definition and be able to translate that into a pre-computed schema. So if you get a view definition from an external source, using this type information, your view runner can look at that, can produce a table that has that using native database types and go from there. And then we also have like a few different metadata where we can attach like arbitrary tags. We're not going to spend much time on the tag stuff just because it's kind of used to flag fields for experimental or additional features going on there. And then under that, we can actually have this select structure is actually recursive. And so you can have nested selects, because sometimes you need to unroll multiple levels of items in there. So, I mean, there's resources that might have, I guess, even in the address example, if you were just trying to unroll zip codes, you might unroll multiple items there. So you could have a select that does a for each, and then underneath that, another select, and so on and so forth. And then I think that touches on, and then there's these options for unrolling those, and then finally, like this union all. So we're going to zoom in on what all these do as we go here as well. So kind of there's the column expressions in that space, name, description, hopefully pretty straightforward in those regards. And I think one sort of tricky area is the semantics for unnesting. And so we'll spend a little bit more time kind of zooming in on the unnesting semantics as they exist here. So in the first one, we'll have like name, date of birth, and everything like that. And then so this is just a single column in that top level stanza. Then in the second stanza, since we're unrolling underneath the name, so if you don't recall in the patient, so there's a name field that is repeated. We want to be able to extract some of the names. And so basically for each name, we're going to create a new row that has that name. So this would create a table that has like a date of birth and repeat that for every row that has that column name. So kind of like you were doing an inner join for this for each. So that's like the simplest case of unrolling thing. We also support, because these are FHIR path expressions, let's say if you only want a table of like official names, we can have a FHIR path expression that simply filters it down to where use equals official and creates that table that only has the official names in it. So this provides like a nice express for this. And as you can see, because it's FHIR path, it makes it nice and concise and pretty easy to understand. Of course, in some cases, you may have patients that don't have an official name in their item, and you may still want to produce a row for that. So we also support this. The only other sort of expansion definition that we have is that we support this for each or null. And you can kind of think of this like an outer join from a database perspective, where we expand, we essentially would expand that name field, but if nothing is there, it would still have a row for that column, that initial date of birth column would still exist for each patient, but the official name, the name would be null in that case. Similarly, like if you were doing sort of an outer join between the base patient and the nested collection there. And that is kind of the sum of semantics for unnesting structures there. And we found that that is actually sufficient to cover basically all the use cases that we've come across as we work through these sorts of things. And the only other thing that's sort of connected to that is the ability to do unions across multiple sub-expressions. And this is the one thing that we added. So if you have, for example, in this case, you want to expand a table that has all the patient addresses and all the addresses of their contacts as well. We can have a union of two selects that must have the same column types, and that just produces like a table that unrolls all of that. So with that alone, like having run this through a variety of analytic use cases, we found that we were able to take FHIR resources and get them into a simple tabular model that's pretty expressive. And of course, deferring to the data to do any sorts of joins or aggregation defers to the database engine, like we mentioned. And I think that, so that gets us sort of past selecting the columns. Now, in terms of filtering it, it's the same sort of pattern where we filtering the resources. We have this where expression. In this case, in this example, we jumped to like a blood pressure resource. Let's say we want to filter all observations to only get blood pressures. So in this case, we actually show the first instance where we'll have the blood pressure code, and you can see just that set as a constant up top, and then we have the FHIR path expression underneath it. So the observation code, we're just seeing if there exists a coding that has the expected system and blood pressure code defined in the constant above. And running this would produce that, and of course, real example would actually have columns and content in the select as well. But just being a FHIR path expression, it works fairly well. And one area that we're kind of exploring that implementations may explore is, for example, if we were to run this against a FHIR server or some other technology stack, what we might do is we could like take that expression and determine, hey, this is something that matches like a code value check and like pre-filter resources as part of this where expression, rather than bulk loading them all. But all that's left to the implementation, and implementations can get more sophisticated over time on how they do that sort of computation and pre-filtering in that space. And then, so the last sort of major piece to all of this is how we do joins. And we have the tables, we've had their filter criteria, now we need to be able to join them together. And so as a result, we've added two additional functions from the FHIR path specification to this space. One is the get resource key, which just returns an opaque key for the resource, and then a corresponding get reference key that given the resource code, whether it's patient or observation or condition, from that reference returns the corresponding key there. And so I think perhaps like the best way to kind of look at that might be to zoom in on to look at a concrete example. And that is like, let's say if I want to create this observation table, or if I have a table of patients and I have a table of observations, I want to join them together, I'll use the get resource key that returns that opaque value as the key there. And then the observation will similarly have a primary key that the observation key will be achieved. And then it'll have that reference key, so our field name is patient ID, and we call the get reference key on the subject field from that observation, targeting like the patient as the reference there. Now, the semantics, the values, how this actually works, how this actually returned for both the get resource key and the get reference key is intentionally deferred to the implementations. In many cases, it may just be the ID of the resource. If you're in a system where every ID is populated and every reference has like a simple ID, that is sufficient for this workload. But we wanted to preserve flexibility there because to work with arbitrary FHIR data. So if you do a bulk export of the system, maybe they don't have those IDs populated, or maybe it combines multiple systems and IDs don't exist in the same namespace. And as a result, we need to do some additional processing in order to determine what that unique identifier is based on like the full FHIR identifier type. And for those of you familiar with that space, you know that can be an evolved step. So as a result, we kind of leave how to do that to the implementations. Some implementations may only support IDs. Some implementations may have a pre-processing step to compute IDs and references for every identifier in this space. The key is if you're authoring a view definition, the semantics here are well defined. You can get the resource key, which is opaque, get the reference key from that. You can store it in the database and join them together arbitrarily from there. All this is well defined on the site, which we'll touch on a little bit there. Yeah, so just like a couple of other pieces that we'll hit here, and I'll save a few minutes for Q&A at the end. We mentioned like the core specification is really kind of focused on being very general. We're actually working on what exactly the profiles underneath that should look like. There's a couple that we have right now. So one is what we're calling the shareable profile. This is just a FHIR profile of that structure definition that it just sets some fields to be required. So it has to have a name, it has to have a URL, it has to specify a target version, that sort of thing. So pretty simple stuff that adds there. We intentionally put that in the profile because if you're authoring a view definition, maybe you don't have this all filled out at that first pass, and we want people to still be able to quickly write and author an experiment without having to be fully compliant. But when they get to the point where it's something to be shared, they can apply that shareable profile and make that shareable. Similarly, with a tabular view definition, we've encountered a few different use cases. We've encountered use cases in which some folks may actually want complex structures to be produced in these output views and produced in these output columns. And so we preserve that capability in the base. However, a lot of systems really require that scalar value per column, and so as a result, you apply that tabular view definition profile from there. And I think that one area that is kind of a work in progress right now is we're going to be working towards what exactly is like this base sort of core profile in the sense that we want to restrict ourselves to a set of FHIR path functions that is probably not the whole list. And that is, again, in the same spirit of making this system easy to build and implement. I think the big one that probably will not be in this core set of FHIR path expressions in this would be the FHIR path resolve, which jumps between resources to resolve references so you can get fields from other resources. The reason for that is like there's quite a few data pipelines and quite a few tech stacks that work really well if I can take a resource and map it onto a table without doing cross-resource resolves. And so as a result, like this core profile likely will not include the resolve. That said, if you're not operating under this constrained core profile, if you're under the base, I mean, resolves are allowed, but you have to realize that it may not be runnable, it may not be by all implementations that exist out there. Again, in the same spirit of using FHIR profiles. So this is like a work in progress set of FHIR path functions that we're likely to have in the core profile. The website is being kind of evolving a bit as we go in that space, so it's not fully reflected there, but that's literally a discussion that a group of us are having this week, and I definitely encourage everyone to participate in that as well, and we'll follow up in those sessions too. And then finally, it's like we have all this is up on the website. So you can go to build.this URL here if you want to explore that. Essentially everything, basically everything I described in this entire talk is up on that website. And you can actually explore around a little bit. I'm on the other screen here, but yeah, you can kind of see in this, see all the documentation there, see some of the examples. And then if we go like over to some of the view definition itself, you can kind of see oops, that's the wrong. Yeah. So if you go to the view definition itself, you can see all the content that we just looked at. All these fields are fully documented, and there's quite a lot of detail in terms of all the semantics, and I can probably zoom in on that a little bit. So yeah, so there's the get resource key and get reference key. The semantics should be well defined there. If there's ambiguity in that, yeah, please let us know. We'll jump into the other spec there. But yeah, we'll definitely want to know about that. So, oops, let's go back to the slideshow. All right. Okay, and so with that, I think that hopefully we kind of see a path forward to making FHIR data in general a lot easier to use with SQL tools, and it feels good. So there's a couple next steps in this space. Is like we're still refining the spec. We're going to target an initial release by the end of July. So input's welcome there. I have links to the spec itself, to the GitHub repository. We're maintaining this as part of the FHIR community process. I think we're mostly up to speed with the new requirements for that space. We're kind of catching up a little bit there, but I think we're quite close thanks to efforts of a number of folks in this room. We also have an active Zulip channel there. And I definitely encourage folks, if you're interested, there's a couple of follow-up sessions. We're going to show multiple implementations, and I believe it's in here in this room at 10:15. And then there's a Let's Build session. I think it's in the Johnson Great Hall over there at 11:15. So with that, I have a few minutes left for any questions that come up, so I will stop there. I saw one hand go up there first, and then I'll do you next. Yes?
Thanks. This is great. I see how this can be used to convert from FHIR to SQL. Are you aware of any initiatives towards converting from SQL to FHIR?
Issues from converting SQL to FHIR?
Yeah.
Yeah, so I mean, I think that that's a problem space that we've not tried to bring on as part of this effort. So I think that if you do need to convert SQL to FHIR, I think and I've been in that space before, there's like a wide variety of sort of ETL or mapping tools, some of which work better than others depending on the use case. So I don't think I can give an informed answer for converting SQL to FHIR other than do a survey of existing mapping tools, which you've probably done.
Gotcha, thanks.
Can you go back to your slide when you show the address and the join in the line?
Yeah.
My question is about the treatment. In the case of the line, you did a join, so all the lines are together. Maybe it's the previous one. No, one more or two.
Okay. Oh, this one.
So, and in the case, no, it's not that one. It's it's a previous one.
Oh, there's one fairly early on, maybe. I can go back to like the very top here.
Yeah, that's one.
Okay.
So in the case of in the street, you join all the lines in the repetition of line, and you have them separated by carry return. But what about the address itself? It will return a new element, or all the addresses will be together in one element? And how do you manage that?
Yeah, so what this will do is like basically every enroll operation here will create a new row. And so in this case basically it will have, the output will be, you can kind of think of it of being implicitly doing like an outer join between, or actually, yeah, implicitly doing a join between these elements. In this case it'd be like an inner join. So we'll have a patient ID, so we'll have one column with patient ID. That value will be repeated for every address that exists here. So you'll have a flat table of addresses. So I think actually maybe yeah, using like this example kind of illustrates that. So you'll see in this case where we have, if patient ID 1 had two addresses, say a home and a work address, it expands their ID 1 and home and work there.
That was and the other doubt is about dates. Usually we have a lot of use cases involving extracting something from the date and showing only the year or the month. That's resolved through FHIR path, or there's any other thing?
Yeah. If it exists in a FHIR path, if you can do it in a FHIR path expression, that would be the way to solve it here. Absolutely.
Thank you very much.
Yeah, thank you. Yes, I think we have one up here. Oh, yes.
Okay, so my question is what you envision for implementations of this spec. I'm looking at this spec and saying, hey, this would be great for what we're already doing, which is taking FHIR resources, dumping them out, flattening them, right? Yeah. It's a nice way to define those table definitions, but we're still copying the data. Are you envisioning an implementation that just takes the view definition, you write SQL, call through some sort of ODBC connector, and it's actually running and making the FHIR API calls for you from SQL?
Yeah, so that's a great question. And I think that's part of the reason why an area that we've intentionally stayed agnostic because different workloads will have different needs in that case. If you have an analysis workload that needs to query 10 million or query a billion observation records, that mechanism probably wouldn't work well. At the same time, if you're doing some interactive exploration against an existing FHIR server, you don't want to set up a massive scalable database. You want a different technology stack. And actually, and in fact, in the showcase that we'll have at 11:15 or 10:15, we'll show both. We'll show there's one implementation that will use like an Apache Spark pipeline. Actually, there's multiple sort of Apache Spark-based implementations that will go through and pre-process and can persist that output so you can scale it at massive scale. There's the reference implementation is actually written in JavaScript, so just interactively query. You give it like a list of FHIR resources, and you can just online play and write it there, so it kind of renders that view online for quick experiments. I know there's another implementation I think Nikolai might talk about in a little bit that at that 10:15 session that computes that will store like the FHIR JSON like in a Postgres database and then kind of build those views on the fly, all based on Postgres. So we're kind of like all over the range there. The key being is like we can reuse these across all those stacks. And so yeah, that's a great question. And actually the fact that there's so many answers to that is exactly what motivated this approach of decoupling the view definitions from them. Okay, so I think we're about at time. Yeah, one more question, and then I think I'll be up here afterwards.
Is there a way to do like a select distinct?
Yeah, so there's not, okay, so great question. So is there a way to do a select distinct? And the answer is no. And the main reason for that is because making this easy to implement, we want to be able to do a run, basically think of it like as like a map function where you get like per resource and expands it to one or more rows. Whereas the distinct, of course, requires like knowing whether it is distinct across other items. So for the select distinct case, this would be an area where like a downstream system, your analytics engine, you might create this full table and then have like a view or a materialized view on top of that makes that distinct, or have an ETL pipeline on top of that makes that distinct. But yeah, that is something that we've kind of scoped out for that trade-off. Okay, well, I think we're at time. We're gonna wrap there. I'll hang out here, and if you're interested, at 10:15, I think, back in this room as well. And thanks so much. Enjoy the conference.